Hello everyone, my name is PARTH and this is my project submission for data cleansing project assigned by Red and White Skill Education as a part of my AI/ML and data science program. In this video, I will walk you through my complete Jupyter notebook explaining every task I performed, the decisions I make, the methods I used, and the reasoning behind each decision. In this project, we have to work with a synthetic patient health records dataset which contains 200 rows and 9 columns with intentional missing values and outliers. My job was to clean this data completely so that it can become ready for machine learning. So I divided my work into 3 parts. Part A, handling missing values with 6 different strategies. Part B, detecting and handling or removing outliers using 4 different methods. Part C, the final and clean complete dataset with a summary report. Let's do it. I am sharing my screen now. First, the dataset. Since this is the healthcare project, I generated synthetic patient dataset right inside this notebook using NumPy. No external files needed. I set the random seed to 42 for reproducibility. This means every time this notebook runs, it produces the exact same dataset every time. This is the professional standard in data science. The dataset has 9 columns. For columns like age, BMI, cholesterol and glucose, I first generated realistic values using a normal distribution, then manually injected missing values and outliers. For example, BMI values of 55, 62, 58, 62, 3.1, etc. These are impossible values in real life. So these are our synthetic outliers. And 18 random position in the age column are set to none, are missing values. Here is our final data set. 200 patients, 9 columns. You can already see some none values in the gender and also in the cholesterol column. This is our starting point. Messy, incomplete and not machine learning ready. Part A starts with task 1, understanding exactly where the missing values are. So to calculate that, I used df.seasonal.sum to see the missing values in each column and then I calculated it in the percentage. So from this summary table, we can clearly see that the highest amount of missing values in terms of percentage are in BMI with 10%. Followed by age at 9%, cholesterol at 9%, glucose at 8%, gender at 7.5% and region at 6%. Patient ID, blood pressure and disease risk have 0 missing values, exactly as designed. Furthermore, this bar chart makes it visually clear which columns needs the most attention. And the heat map below shows where in the dataset missing values are scattered. Each yellow cell is a none. The pattern is random, which is what we want in a well-designed dataset. Task 2, imputation. I have applied 6 different strategies, but let's start with the simplest one, the SimpleImputer from scikit-learn. So for the mean imputation, I created a SimpleImputer with strategy is equals to mean. Then the fit_transform method scans the data to calculate the mean, ignoring the none values for each column. Then replacing that mean value with each and every none value. As a result, df_mean is underscore field has no missing values now. Then I did the same strategy. I did the same with strategy is equals to median. Why median? Because BMI, cholesterol and glucose have extreme outliers, values like 55 or 430. The mean gets pulled by these extremes, but the median stays in the center of the distribution. So for skewed data, median imputation is more accurate. This side-by-side histogram shows the difference. The side-by-side histogram shows the difference. You can see the mean imputed BMI has a slightly right forward shift due to those extreme values, but median stays cleaner. Moving forward, for categorical column like gender and region, mean and median have no meaning. So I used strategy is equals to most frequent, which fills the missing values with the mode, the most commonly occurring category. So through that, the imputer learned that the male is the most frequent gender and north is the most frequent region. So all 15 missing gender values were filled with male and all 15 missing regions with the north. The bar chart clearly shows that after imputation, the non-bar disappears and the male count increases. Since only 7.5% was missing, the distortion is minimal and acceptable. So, this section covers two techniques together. First, the missing value indicator. Instead of just filling the none, I also created a binary flag column for each column that had missing value originally. For example, age was missing is 1 if that patient's age was originally none and 0 otherwise. Why is this useful? Because the fact that a value is missing might itself be informative. Maybe patients who skipped the glucose tests are healthier. So the machine learning model can learn from this pattern if we explicitly tell it that where the missingness was. Second technique, random sample imputation. Instead of filling with the same mean every time, I randomly sampled values from the existing non-null values of each column. This preserves the original distribution, no artificial spikes at the mean. I used replace is equals to true for the sample call. This allows the same values to be picked multiple times when we need more field values than available data points. After this, 0 non-values remains in the column. So now for multivariate approach, the KNN imputer. KNN stands for K nearest neighbors. For each missing value, it finds the 5 most similar patient based on all their other attributes and find those missing values from these neighbors. So I here used weights is equals to distance, meaning patients who are more similar to the target patients have a bigger influence on the estimated value. This is smarter than treating all 5 neighbors equally. Look at this comparison. Mean imputation creates an artificial spike at mean value because every non got the same number. KNN gives a smoother, more natural distribution because each missing value got a contextual appropriate estimate. KNN is clearly more accurate for this dataset. Moving forward, the most advanced imputation method that I used is MICE, multiple imputation by chained equations, implemented as IterativeImputer. Important, this first line is mandatory. Without it, importing IterativeImputer will fail with an error. This is an experimental line that needs to be unlocked explicitly. MICE works iteratively, one column at a time. All other columns are predictors. This repeats this process for 10 rounds until the values coverage and stabilize. So if BMI is missing, MICE uses age, cholesterol and glucose to predict it. This continues the real biological relationships between the medical variables. These 4 panel charts, as you can see, compares KNN and MICE distribution for all the numerical columns. MICE is the winner, most statistically accurate. I used MICE as the base for all the outlier works. Now part B, outlier detection. I used 4 different methods, each on different columns. First, the z-score method. Z-score measures how much a standard deviation far a value is from a mean. I set the threshold is equals to 3, which means any value having an absolute z-score greater than 3 is an outlier. This is the z-score formula applied to every row. A cholesterol of 420 gives a z of about 6 to 6 standard deviation above average. That is clearly an extreme outlier. I applied z-score to cholesterol and glucose, the columns with most extreme values. The method correctly identified 3 cholesterol outliers values of 420, 8 and 430 and glucose outliers values of 380, 400 and 350. After removing those 6 rows, the distribution is clean and realistic. The before chart shows a right tail from the extreme values. The after chart is properly bell-shaped. Second, the IQR method. IQR stands for Interquartile range, the spread of the middle 50% of the data. I applied it to BMI. The standard 2 key fences any BMI below Q1 minus 1.5 times IQR or above Q3 plus 1.5 times IQR is flagged as an outlier. This method is robust to skewed data, as it uses percentile, not mean or standard deviation. so extreme values don't distort the boundaries. The box plot on the left side shows extreme dots above and below the whiskers. Those are our outliers. The box plot on the right after removing them has clean whiskers with no extreme points. BMI values of 55, 60, 62 and 3.1 are gone. Third method, percentile. I applied this to blood pressure. I defined the valid range as 1st to 99th percentile, which means any blood pressure reading outside this range will be considered as the extreme outlier. The method correctly detected the 3 blood pressure values we planted: 215, 220 and 230, which are medically at the level of hypertensive crisis and clearly wrong for a routine patient record. After removal, the blood pressure distribution is clinically normal. Fourth and final outlier method, Winsorization. This is fundamentally different from the other three. Instead of removing outlier rows, it caps them at boundary values. Any BMI below the 5th percentile is raised to the 5th percentile value. Any BMI above the 95th percentile is lowered to the 95th percentile value. No rows are deleted. The dataset size stays the same. I showed both pandas.clip and SciPy Winsorization method, two tools, same results. See how count is identical before and after. That's the key advantage of Winsorization. Zero data loss. Moving forward, here's the complete before versus after picture. Originally 200 rows, 99 missing cells, cholesterol max of 430, glucose max of 400, BMI max of 62 and blood pressure max of 230. After all cleaning, 0 missing cells, cholesterol max dropped out to around 280, glucose max around 170, BMI max of 38, blood pressure max around 165. All values are now within clinically realistic ranges. This grouped bar chart makes the improvement visuals. The red bars are before, green bars are after. The dramatic drops in max values proves the outlier handling works. And here is the final clean data set. All distributed, look natural and medically possible. 0 missing values, no extreme outliers. This data is fully machine learning ready. So that's it. This was the complete walkthrough of my Jupyter notebook. To summarize, in this project, I demonstrated 7 imputation techniques and 4 outlier handling methods on a synthetic healthcare dataset. In my conclusion, mice was the best imputation strategy as it captures multivariate relationships between medical variables, and Winsorization was the best method for data preserving as it is the best quality and also it doesn't remove any rows. So the complete source code, this video and readme are all available on my GitHub repository link. The link is in the readme file. Thank you for watching. This is PARTH, signing off.